So this is the Mark V shutdown circuit. We're going to be going through each part of the shutdown circuit on the car and trying to identify where it is and what it does. We aren't going to assume prior knowledge of the vehicle or electrical engineering where possible. We won't be looking at schematics or PCB layouts, but we will start building a system level understanding of the shutdown circuit. We won't be looking at abstract system diagrams or block diagrams. We'll be talking about each component of the shutdown circuit in the context of the car as it exists right now. Today's learning goals are that you should be able to understand the purpose of the shutdown circuit, be aware of the FSAE rules relevant to the shutdown circuit, understand the operation of the nodes on the shutdown circuit, name and identify the nodes of the shutdown circuit on Mark V, and be comfortable working with another engineer to debug a fault in the shutdown circuit. So this is just like the most basic level of circuit stuff that we're going to be talking about today. Current is the flow of electric charge through a conductor. Voltage is an electric potential that exists between 2 points on a circuit. We call a circuit open when it's not connected, which means current cannot flow. We call it closed when it's connected, which means that it is possible for current to flow. We'll also sometimes say that a circuit is complete when all of the nodes in a larger circuit are closed. And an interlock is an element of a connector that closes a secondary circuit when the connector is attached. That's a fancy way of saying it's a feature in some connectors that allows us to tell whether they are connected properly or not. The relevant technical terms for today are the accumulator, which is the FSAE term for a battery pack. Technically, it doesn't have to be a battery pack, but the reality is every team out there, it means battery pack. And something to notice here is we'll have rules call out sometimes. So these are references to the relevant rules in the 2020 rule set. So if you want more information about something at a later time, you can look up those rule numbers and get the official rules text on the relevant items. The tractive system is every part that is electrically connected to the motor and or accumulator. So for us, that mainly means the motor controller or inverter, and the accumulator, the battery pack. But there's also some other small components that are rules required here and there that we won't cover today that technically are part of the tractive system because they're part of that high voltage circuit. Grounded low voltage is the overcomplicated FSAE term for everything except the tractive system that's electrical. And it's called grounded low voltage because all of those components have to be grounded to the chassis. And then finally, the accumulator isolation relays, or you'll often hear them referred to as airs, are two large relays that separate the accumulator from the rest of the tractive system.
I want to add something. Tractive system is generally referred to any high voltage that's after the airs. Just other things to remember.
Mm-hmm. And so why does this matter? If we look in the rules, we see that the shutdown circuit must directly carry the current driving the accumulator, isolation relays, and the precharge circuit relay. This is a fancy way of saying that the airs cannot close unless the shutdown circuit is complete. And to what Dasha was saying there, that means that high voltage cannot enter the rest of the car unless everything on the shutdown circuit is working. And they also say that the team has to be able to demonstrate all of the features and functions of the shutdown circuit during electrical tech inspection, which means that the shutdown circuit ends up being a very large part of E-Tech. And so I think all said and done, the shutdown circuit is the most likely part of the car to prevent it from operating at any given point in time. There's 16 points of failure across the shutdown circuit. And it is one of the most scrutinized areas of the car. So it's a really good area to feel comfortable kind of knowing what's going on. As we go through it today, we're going to be going through the nodes in order, which is literally the order that they are wired up in the car. Most of that order is completely arbitrary. When the rules require a certain order, I'll make sure to point that out. But it's worth understanding that any node on the bus can be open at any time, and any combination of nodes on the vehicle can be open at any time. And due to how the circuit operates, if a node early on in the car is open and the circuit is broken, the vehicle is not able to detect a later break in the circuit without you manually looking at it. So you're never going to see like 3 separate nodes giving you an error. You're going to see an error, and everything after that is going to be an error. So when debugging, it always is effective to find the first node that is broken or open, start debugging that, and move down through the rest of the shutdown circuit until you reach that. So the shutdown circuit starts with the low voltage battery. On Mark 5, this is mounted on the back right of the chassis. This diagram is oriented such that what I call left and right are going to be swapped. When I say left, I'm going to mean the driver's left. And this is obviously top to bottom. So the driver's left is on the right on this diagram, just to make things more confusing. So there, it's hard to see, it's right. Can you see my mouse? Awesome. Yeah, right here, this kind of box hidden below some other stuff is the low voltage battery that we use for the shutdown circuit and most of the low voltage systems. We also have some cooling batteries which look identical and are mounted in similar positions. And they are just kind of they are not directly part of the shutdown circuit. So this low voltage battery gives us 12 volts out. We say 12 volts, it's technically more like 12 to 16 volts, which is something that's always important to like check components when you're looking at data sheets, that they can actually take that potential 16 volts of a fully charged battery. But that starts the shutdown circuit. And so assuming our battery is charged and hasn't been absolutely destroyed, we have battery voltage at the start of our circuit. The first node on the shutdown circuit is the grounded low voltage battery fuse, which is a fuse that protects the entire battery from overcurrent faults. So fuse is a component that will break a circuit if there is a flow of current greater than some certain design parameter. And so the rules tell us that all electrical systems have to be appropriately fused. And if you look at EV 7.6.2, it dives into the like, how do you calculate this? What is appropriately fused? Like what are those numbers and what are the calculations you should be doing? So that fuse is directly after the battery inside of the low voltage box, which is this enclosure here. And that is the first thing after the battery before it touches any of our electronics, which is important because A, rules required, and B, it means that if there's a short circuit anywhere in the car, that fuse will blow before we damage something important. The next node is the grounded low voltage master switch. This you'll see on the side of the car. This is the right side to the driver. It is a switch with a red circle on it, and it will have this big red key in it. The grounded low voltage master switch not only is part of the shutdown circuit, but it is also the switch that completely turns the low voltage systems on and off. And its rules required that the current of the shutdown circuit flows through the switch. And then there's a lot of specifics on where do you have labels, what do the labels say, what symbols do you use next to it, how big is it, how high is it, a lot of boring stuff. that can all be found in the rules. So assuming both of those are working, we have another fuse. This is the shutdown main fuse. We have a second fuse because our circuit branches off into the shutdown circuit and then some of our other low voltage electronics. And again, we want each system to have a fuse where possible, because that allows us to have a smaller fuse that protects a single part of the system, so that if there's a fault in one part of the system, we're able to contain it to a smaller area, which helps us diagnose where it is because we can find which fuse tripped. And it also means that if something goes like terribly wrong, it is less likely that a fault damages something in a larger section of the car. And so this fuse is just for the shutdown circuit. And that is mainly because a lot of current will flow through the shutdown circuit when the airs close, but it's also a huge part of our car. And so it's a pretty likely place for there to be like a wire nick or a short circuit somewhere. And so we want to make sure we could isolate that. The next two nodes on the shutdown circuits are both emergency stops. The mounting, placement, and labeling of these is, as always, rules required. The rules will often call these shutdown buttons, which is a much more like FSAE specific term. E-stop is the term that you'll see in like almost any type of project where you have big red buttons that turn the system off. So that's the term we use on the team. Activating any of the e-stops on the car obviously shuts it down immediately. And so there's one on each side of the chassis, there and there. And then later we'll look at, there's one on the dashboard so that the driver can stop the car if they need to. The next node on the shutdown circuit as we move forward in the car is the TSMP Interlock, which is the Tractive System Measuring Points Interlock. The Tractive System Measuring Points are a rules required element of our design, which allows you to safely measure the voltage of the pack outside of the accumulator. And it's important that these are interlocked because any high voltage connection is rules required to have an interlock, as it would be extremely dangerous if a high voltage connector came undone or was not properly installed and the car still turned on and high voltage left the accumulator. And so this is a safety measure where if a connector were to ever come undone or not be installed properly, it just won't turn on and the airs won't close. The brake system plausibility device is where we start getting into some of the more not just a button or switch type of things on our car, which is what most of the shutdown circuit is. There's lots of rules about the operation and implementation of the BSPD. I think the most interesting or important element of that is that it's necessarily that it is a non-programmable circuit, which means that we can't have a microcontroller or firmware operating as part of the BSPD. So we have to implement it completely with like discrete circuit elements. And the goal of the BSPD is to make sure the brake sensor is behaving in the expected fashion. And if the brakes are being pressed, we are not seeing acceleration. So the BSPD will throw a fault if the driver has pressed the brakes and we see sufficient pressure in the brake lines, but we're still seeing a torque request and the motor's spinning. And that's just like your simple, you should not be able to accelerate and brake at the same time. Obviously that is bad for any vehicle. And this is both prevents that and make sure that if something fails miserably and you're pressing the brakes, but they aren't engaging, the motor is going to cut out so that you aren't stuck with no brakes in a race car. It's unfortunately not depicted in CAD, but the next element is the inertia switch, which is also sometimes called a crash sensor. It's basically a device that is rated so that if there's a very specific force that is exceeded, I think it's like 8 to 10 Gs of acceleration, it will break the circuit. And this allows us to detect, in theory, if the car has gone into a wall or other object at a high speed, and shut down the car if that happens, which is mainly important because if there's an accident, you want to make sure that you de-energize the car so that someone who is attempting to help the driver is not at risk of a shock. The BOTS, the brake over travel switch, is literally just a switch that sits behind the brake pedal. And this ensures that if we lose pressure in the brake lines and you are suddenly there's no resistance in the brake pedal, and so you're able to push it all the way past how far it should be able to go under normal conditions, this will trip the switch. Again, if you don't have brakes in a race car, we need to turn it off. Nothing good ever happens when you don't have brakes. And this also has to be implemented with analog components and non-programmable logic. It turns out that like this literally can be a switch. Like it's very simple. That's why it's called the brake over travel switch. The final e-stop is the driver e-stop, which is mounted on the dashboard panel. We don't have all of the elements in CAD here, but there is the driver e-stop, and then there's a number of indicator lights on the panel, all of which are labeled and rules required, and those will give you fault indicators for certain very worrying faults. So the stuff that like if it's going wrong, you need to behave differently. Like the BMS is reporting an error, something is like potentially dangerous with the cells. There's a light there, and that means that A, the driver will know, and B, if you're ever troubleshooting or debugging the car, it's a great place to look to immediately get some feedback about what's going wrong with the car. The next three are more interlocks. And so the same rules as kind of all the interlocks apply here. The first one is the high voltage disconnect, which is a switch. If you see it on the car, it has like this orange rotating handle. When you rotate it, it breaks the circuit. And so it's a really fast way for someone who is coming to the aid of the driver to disconnect the high voltage system and ensure that it is safe to approach the vehicle. The HVD in many cars, you'll see it directly on the accumulator. However, due to the rules requirements about the height and accessibility of the HVD, we have what's called a remote HVD, where we actually run a set of wire from the accumulator to our little HVD box here. But we have both a interconnect on the HVD itself, so we can tell if you've pulled that connector out. And we have an HVD on the connector where it actually attaches to the accumulator to ensure that it's properly installed. Next to that, we have an identical connector, which is what actually connects to our motor controller. It's called the main pack connector, as that's where kind of the load of our vehicle is going to be attached to the pack. And per rules, this also has to have an interconnect. Finally, we start getting into the stuff inside the accumulator. The battery management system, you'll also see it referred to BMS or AMS for accumulator management system in the rules. Monitors cell temperatures, cell voltages, as well as a number of potential faults that can happen that potentially indicate a unsafe condition in the battery pack. And if any of those happens, it will break the shutdown circuit. There are way too many rules to really summarize. So definitely, if you want to see the rules relevant to the BMS, looking at that EV 8.3, there's like 2 to 3 pages of rules, which is a lot in this context. Like that's a lot more than most things, but it's very digestible. It takes like 15 minutes to kind of go through and start getting a sense of. And then the IMD is the installation monitoring device, which is a part we buy from a competition approved vendor. And it is able to detect an isolation failure, which means that there is a current path between the tractive system and the grounded low voltage system. And this is a really important safety measure because the entire chassis is connected to our grounded low voltage system. So if that becomes connected to the high voltage system, it suddenly becomes very, very likely that anybody touching anything on the car would potentially get shocked. And so this will make sure that we we open the airs and disconnect everything if that happens. And the somewhat interesting design note here is it requires that it is monitored without any programmable logic again. However, the IMD does not give us a convenient signal out of like things are good, things are bad. It actually has a communications protocol. So there's a circuit on the car called the IMD latch, which ensures that if it starts trying to talk to us, telling us that something's wrong, we consider that a fault and we open the shutdown circuit and stop anything from happening. And then finally, the last element of the shutdown circuit, which is the only one that's order is mandated by the rules. Most of these things are things that the rules explicitly tell us we have to have, and we have to do a certain way. But the rules tell us that the tractive system master switch has to be the last switch before the airs, except for precharge circuitry and interlocks. We decide to have it as the last thing before the airs, except for the precharge circuitry, because it ends up working out pretty well based on our layout. And it also is pretty convenient for debugging, having your master switch be the last thing so that you can debug everything up to the switch before you attempt to turn the last switch. Switches are pretty easy to debug when the car turns on. And so if all of this is functional, that means that suddenly we've closed all of these nodes of the shutdown circuit. And so now the 12 to 16 volts of the low voltage battery is connected all the way to the part of our circuit, which we call shutdown final. And that is what is used to drive the airs closed, as well as the pre-charge relay that the rules mentioned that we'll talk about more next week when we look at the shutdowns or the service section. Today's the shutdown circuit. So before we kind of wrap up and get to some Q&A, a few quick debugging tips. If something with the car is ever not working, the first thing I look at is the tractive system active light, or TSAL. It will be green and solid when there's less than 60 volts outside of the accumulator and the tractive system, and it will be red and blinking when there's more than 60 volts. So in theory, if it is green a few seconds after you have turned the tractive system master switch on, it should only take about 1 second for high voltage to enter the tractive system. If it's still green, that probably means that the shutdown circuit is not complete and you should start looking at the shutdown circuit. If you're able, the easiest thing always is to get CAN from the car. We have a command line interface, a number of open source tools that we're able to use, as well as a GUI that's being built, and some other things that people have built out that let us see the status of the car over the CAN bus. This is the communication protocol we use for everything, and it lets us tell whether there's BMS faults, whether boards are complaining about things, or if any of the shutdown nodes that we have sensors on are open. And so most of the time, if you can quickly get CAN from the car, it will tell you which node is the problem, and you can start your debugging right from there. If getting tan isn't feasible, or it is telling you something and you've checked that node and it seems like it's working, the indicator lights on the dashboard and in enclosures are a good bet always. And if all else fails, you can check nodes manually, which just requires finding the purple wires going in and out of it, turning off the car to make sure that there is no chance of you potentially shorting something or damaging it. And then you can use a multimeter to measure conductivity or continuity or resistance across that node in the shutdown circuit. And you'll either see a beep or a very small resistance if it's working. Otherwise, you'll see a big resistance or it won't beep. And this means that you can kind of go through node by node very quickly in this order. And even if everything else is broken, you can identify where your shutdown circuit is operating. And then final kind of warning is that I didn't cover all of the details of resetting the shutdown circuit and some other rules. The rules are very particular about like what can you do if the shutdown circuit is open, what is required to reset things and attempt to close it again. When can certain nodes open or close? Certain nodes have to be like a relay or this or that or the other thing. And so nothing is a substitute for reading the rules. Hopefully this presentation is a pretty solid reference. But if you're designing something or troubleshooting something and there's kind of an outstanding question, or it's like, why did we do it this way? It's possible that there's another rule that specifically says something about that. And that is the end of what I had prepared presentation-wise. So if anybody has any questions or parts that they'd like to have more information about now, we definitely have some time for questions, feedback, whatever you feel like.
A question I have is, why isn't precharge included in the shutdown circuit? Because if precharge fails, wouldn't you not want to close the errors?
Yeah, so this is the kind of like asterisk that we'll talk about more when we look at the service section. One of our two errors closes when the shutdown circuit is complete. The other we close with the service section board, so it doesn't close automatically. And that's because we don't want it closed while we're pre-charging. And so if pre-charge never completes, we will never make the decision to close that second air. So the shutdown circuit is not the only thing that is required to close the airs, but it is required to close the airs. We can't close the airs without it, and it's the most likely thing to prevent them from closing. But that is a good point that, yeah, we can't continue if pre-charge isn't complete.
That makes sense.
I have a quick question. I was just wondering if you could speak a little bit more on the difference between the HVD interlock and the HVD connector interlock, because I know that like one is like for someone coming to the car, it's like the orange gearish thing on the back, but like the other one where it feeds into the accumulator, how does that close itself automatically, or open itself automatically when the shutdown circuit needs to shut down, or is there something we have to do for that as well?
Let's see. Okay, so yeah, we have the HVD interlock, which is the the explicitly rules required one. Yeah, an interlock must open the shutdown circuit when the HVD is removed. So that ensures that if we remove the HVD, we not only lose high voltage by breaking the circuit, but we also open the airs so that it's safe to interact with. The HVD connector interlock is required based on the fact that it is a connector outside of a housing. And so all of those high voltage connectors need to have an interlock. And how the interlock works on these connectors is they have two small pins which are shorted together. So if we put the shutdown circuit into one pin on the inside of the accumulator, and then we take the shutdown circuit out on the other side, the shutdown circuit will only be completed when the connector is put in. Otherwise, it's just an open circuit. And so it's like a very kind of simple way to detect that, oh, this connector is plugged in. But it basically guarantees that the shutdown circuit won't be complete unless all of the connectors on the car are installed fully. So you could also, like, unplugging that connector would have the same effect as removing the HVD. It would just be a bit more of a pain in the ass to do. Because it's, you know, underneath the driver's seat, in between some steel bars.
Something you brought up was that we can't have any firmware in the BSPD. If we can't have firmware there, how do we stop requesting torque from the motor controller? How do we like send that signal? Is that different or?
Yeah, that's something, good point. BSPD, the circuit that breaks, that detects the faults and breaks the shutdown circuit has to be non-programmable, but we have the microcontroller on that board is able to detect when the BSPD circuit faults, and it is able to use that to then stop requesting torque and respond, you know, publish the fault to the CAN bus, do anything we want to. The rules just care that if that microcontroller died, the shutdown circuit would still open when the BSPD fault happens.
Okay, that makes sense. So like just like the actual node of the shutdown circuit can't be firmware dictated, but other parts can be.
Yeah.
Okay.
Also,
And
like the support. Oh, sorry. Go ahead, Elvis.
No, yeah, it's just basically the competition doesn't check your firmware in any way. They check all of your schematics and PCBs, and they decide like, we're never going to understand your firmware well enough to check it. So whenever they're worried about something not being safe, they're just like, you can't have firmware because we can't check it.
Right.
It's also worth to note, like, since the shutdown circuit is explicitly to open the areas in case anything goes wrong, which allows us to provide power to our motor to actually spin. So when we're cutting that power, the motor shouldn't be spinning, which means that if we press the pedal, it shouldn't be going forward. But everything else that Elvis said is also correct.
And that's where the rules do allow. And if you look at the schematic, there's like a timing circuit built in that you're allowed to wait up to half a second before you actually recognize the fault, which is to basically give you like a little bit of wiggle room of like sensor lag or parasitic capacity or anything that could mean that like for an instance it says that something's going wrong even though it's not quite. And it's also convenient because that little bit of time means that in theory the passive discharge circuitry should mean that our bus voltage is already dropping to a safe point by the time that the BSPD is faulting and we're opening everything up and panicking.
Something else you mentioned was that like we have to be able to prove that if there's a fault in any of the nodes during ETech that it will throw a fault. I feel like, how do you do that for someone like, I don't know, like the IMD that's like trying to detect shorts, or like, could you just like go through like some of the non-obvious ones?
Yeah.
Detect that.
I think I can go through basically all of them. So some of it is that things that we put in the shutdown circuit that aren't rules required to a degree, or like the rules don't consider officially part of the shutdown circuit, we don't have to test. So fuses, we don't have to demonstrate that, like we don't have to blow the fuse somehow and be like, oh, look, the fuse blew. in the like electrical safety form, you give them the calculations and data that show like we spec this properly. They trust that the fuse is going to work. So I think the fuses are kind of the exception of like, we don't have to test this at all. Switches, as you said, pretty obvious. You just like turn it on, turn it off, see if it works. The e-stops fall under that. Interlocks, you know, an easy way to test that is unplugging the connector and then showing that the shutdown circuit doesn't complete. And that they also, I don't know how rigorously they check interlocks in eTech, because I think they request the data sheets on your ESF. And so it's a rules requirement that your data sheets show connectors that have interlocks on them. Or if it's a connector that doesn't have an interlock, you are able to demonstrate that you have built an interlock into the connector. Like our TSMP connector doesn't technically have an interlock. We just short two of the pins together on one side and we call it an interlock, and we tell the judges that we did that. BSPD is the like most probably difficult one to test, as you kind of identified. The way that we test that is that we have a wire that runs through the current sensor for the BSPD, which is how the BSPD tells that there is still the motor is still receiving a torque request. Is there current flowing to the inverter, the motor controller? And so if you run a wire through that and then loop it back out of the accumulator, we can hook it up to a artificial load, and we can force a bunch of current through that wire to simulate current flowing. And then we can, there is a test switch built into the board that allows us to simulate the brakes being depressed at the same time. And the rules actually give guidance on how to do that, which is nice.
One thing to note though is that in previous years we had that test switch, but in like this year they said to change that and to have like the current sensor be directly like involved in the test circuit. Because usually we would like simulate it and then it would like do its thing and open or close the shutdown circuit. But now they're like, no, it needs to be, we need to check that the sensor is actually incorporated in that circuit, which was an interesting thing to figure out this year.
And that's one that was like a pretty recent revision to the rules. And that falls under like, there's a good, they probably had a team that showed up and was like, look, our BSPD works. And then it turned out that like the current sensor was busted. And so somebody had to write a rule to make sure that didn't happen again. Inertial switch, literally the way they want you to test it is like, I think shake it really hard and show that your switch is like not permanently broken. And then it's resettable. So you shake it, you show that it, oh, look, the switch went off, then you reset it. Breaker over travel switch, we can demonstrate by like showing that with the brake lines pressurized, you aren't able to activate the switch. And then I think we have like the documentation that this is in fact close enough that the pedal will eventually hit it. It's possible for it to engage, and we can test it by flicking it manually. Another e-stop, interlock, interlock, interlock. BMS, I believe we are allowed to just, I don't actually remember off the top of my head. I don't think during tech inspection they require you to simulate a BMS fault.
Yeah, they don't. What they want to see is to demonstrate that your BMS is working, which means, what we did was show them that we're actively monitoring the cells and that they're in the safe ranges, and then just explain to them how we're communicating and as like opening and closing the shutdown circuit based on that. They're not gonna, they won't ask you to induce a fault in the BMS because that could be pretty dangerous. Like, yeah.
waiting for the tech inspection where you have to demonstrate a temperature fault in your BMS, a short in your battery pack. IMD was a really good question because, as you said, it seems like it'd be really dangerous to test that in any way, and it would be. They have a fun magic box that they stick into your TSMPs, which is one of the reasons why the TSMPs exist. And it allows them to create a fault in a safe enough way because they kind of have some safety factors built into it. And you're doing it at tech inspection, so they make sure everyone's, steps away from the car, no one's touching it. And so literally they plug in the IMD test box, they induce a fault. The rules give you up to 30 seconds for your IMD to trigger, which is like crazy. But they wait up to 30 seconds. They see, did the IMD light on your dashboard turn on? Did the shutdown circuit open? And that's the test they do for that. And then finally you have another switch, flip it on and off. And so that testing is like, most of it is pretty straightforward. Like literally we need to flick a switch. It ends up, I think it ends up being a pain, mostly because there's so much. And so E-Tech, literally just going through that takes a long time. Especially because the judges are gonna probably be asking you questions about it as you go. So you're gonna demonstrate it and they're gonna be like, can you explain this? Because they want to check everything in every way they can. And so if there ends up being a issue with our shutdown circuit during tech inspection, and we then have to debug that during tech inspection, it can kind of be this cascading of then, okay, we need to figure out which node has the issue. And then we need to come back and start going through all of the nodes after that node again and demonstrate that they're all working.
Another thing to note is that for a lot of these, if not all, you're closing the errors and opening them again and again and again. So there's a note on the tech inspection sheet that says the teams can dictate the pace of this test, because if you're constantly opening your shutdown circuit, it can you might not complete discharge or precharge fast enough, and it's just, you want to make sure that everything is in a safe condition before you constantly turn it on and off. You don't want to break components during tech.
Yeah. And so that's actually that's a really good point. That is one of the dangers. And that was a piece of analysis we were slightly missing. They say you can set your own pace. And so we want to make sure we're setting a pace that gets us through tech as fast as we can reasonably, but also doesn't put us at a risk. If we don't need to wait a minute between doing a pre-charge discharge cycle, we shouldn't be. But if our heat sinks are getting really hot, we do need to be careful. I think that in Mark 4 tech inspection, I believe I was told that it got hot enough that the pre-charge resistor desoldered itself from the circuit board because it was hot enough that the solder just melted. And so it's definitely something to be aware of. We have some thermal numbers for this year, which suggest that every time we do a pre-charge discharge, the temperature of the heatsink increases about 4 degrees, which isn't that bad. We could go through probably the shutdown circuit pretty rapid fire and be safe, but that's definitely something that at our mock tech inspections next year, if we can have a temperature gun on those, which they won't allow us to do while we're in tech inspection because the accumulator needs to be closed and installed. That would be great data to get of, RMI, not a Mechie, never taken thermal calculations, anything good at all.
Is there any way to check if the errors are working properly? Does that have to be done physically or?
Checking. So we have the errors have an auxiliary contact. So which means that when we close, they complete 2 circuits, one for the high current path and then one for a 12 volt circuit that we can use And so we put 12 volts into that auxiliary contact, and then we read out what we're getting on the other side, either high or low, on the air control code. And that allows us to detect what's called an air weld, which is when we stopped closing the air, but it still stopped closed, which is obviously a fault because that's potentially dangerous. And it would also allow us to detect, like, okay, we have attempted to close the air, but it has not closed. That then leaves us like, oh, it could be a wiring error. Maybe the air isn't actually getting 12 volts from the air control board. Or it could be obviously like the air has somehow died. They're rated for like 100,000 cycles, but it could happen, especially if we have like a high current discharge event, which we've done. So then you're just stuck like getting on HV gear and pulling out the tools and trying to figure out why it's not actually closing.
If the air is weld, how do we like manage that situation? Because doesn't that mean that we can't disconnect the high voltage from the rest of the car?
Panic. Yeah, that is a really bad failure mode.
Right.
And it is something that is accounted for in the pre-charge and discharge circuit do a lot to make sure that it's really hard for that to happen, because it would take a ton of current to weld an air. I forget what they're rated for, but it's like plenty more than we're doing. The main protection factor there is the main pack fuse, which is the $100+ fuses we blew at competition. In theory, those fuses should blow far before there's enough heat on the air contacts for them to weld.
Okay.
But it's a possibility. I actually think that that's something to consider, that we should maybe have a warning light of some sort if we detect that, because if that were to happen, we would want to pull the HVD immediately. But it'd be important that like the driver doesn't attempt to get out of the car until that's done.